Hello, my name is Steve Langevich, and today we're going to talk about DNS, which really is the backbone of the internet, and without it we wouldn't be able to use the internet as we do today. So basically, DNS allows a IP address to have a human readable name. Now this is important because if we didn't have an easily rememberable name, we'd have to go write down numbers and memorize numbers. So say if we wanted to go to yahoo.com, we'd have to type in 98.138.253.109 every time we wanted to visit it. But with DNS, we can simply type in yahoo.com, and the service takes care of the in-between, getting that IP address for us. So we'll first talk about how DNS works to get a IP address. So in this instance, we have our client computer here trying to go to yahoo.com. It checks its local cache to see if it's been there before, see if it already knows the IP address. If it doesn't, it's going to refer it to its local DNS server, which has recursion enabled. With recursion, it's going to go out and find the answer and then give that back to the client. It's going to do all the legwork and give the client the final answer. So our laptop asks, where's yahoo.com? The local DNS checks its local cache as well, finds it doesn't have the answer. So then it sends a request out to the root server. And it's going to ask, do you know where the yahoo.com web server is? Now the root's not going to know, but it's going to know where the top level domain where yahoo.com is kept in, which would be the .com server. There's also a .org server, .edu, .biz, all kinds of top level domain servers. So it's going to reply the address to the top level domain server to the local DNS, which will then take that number, go out to the .com server and ask the same question, where's the yahoo.com web server? It's not going to know exactly either, but it'll know where the next domain server, the name server, will be that knows. So it's going to reply that address. Our local DNS will then go back out to the yahoo.com domain server, and it's going to ask, do you know where the web server is? Now, being authoritative in the yahoo.com domain, it's going to know where the web server is. So it's going to reply to our DNS the IP address of the web server, the 98.138.253.109 IPv4 address. Now, that's the main purpose of the DNS, to get that final IP address. So it's going to give its results over to the client. Hey, yahoo.com is at this address here. Then the client will go out in its web browser to that IPv4 address, and it'll reach yahoo.com, and that'll reach the website it was looking for all along. Now I'm going to show you how DNS is used in my local network. Now this is a drawing of my network I did for IT130, and it has multiple subnets and an internal and external subnet. So on the inside here, the very inside, is going to be VLAN 10. Now this holds my domain controller with a DNS server included, because Active Directory requires DNS, which we'll talk about more in a moment here. In the next VLAN, we have VLAN 5. This is kind of in between our internal and our external, but it's not quite a DMZ zone yet. Inside here we have a read-only domain controller along with DNS. That provides redundancy in case server 2 goes down. There's still a server that knows basically a copy of the domain controller on the network. So that way clients can still sign in and access resources. Going out into the red zone here is what is considered the DMZ zone. And this holds all the servers that would have direct access to the internet, or where clients on the internet would access our services. Here we have 3 DNSE servers, external servers. And that's to provide redundancy in case one of these go down. Web users can still resolve our IP address for our web server and still access our services. So we have 3 of those here, as well as a web server, which hosts our website, and also the host machine that I use in the class is on here as well. And this is the only physical machine that hosts. Everything else on the schematic is internal, or is virtual machines, all ran in VMware. Now, on this next slide, we're looking at the servers with fully qualified domain names. And this is where DNS comes in. So, say I'm on this workstation here, and I wanted to access server 2. I can type in server2.anishnaabemowin.com, and it's not going to know the IP address right away. It's going to have to check with a DNS server, kind of like how we showed with yahoo.com. But instead of going out onto the main internet with the main host servers on the, or the root servers on the internet, it's going to go to basically server 2, which has the DNS server on there. It's going to ask, do you know the IP address for this server2.anishnaabemowin? And it's going to look and it's going to say, yeah, it's going to be 192.168.10.2. And then it's going to send that back to the workstation. And then once it has the IP address, they can talk to each other. Now, they can already talk to each other because on this workstation, DNS is set up to go to that IP address every time. So, even though it was trying to resolve the name of server 2, it was still pointed at server 2 to use DNS. So it still had a connection either way. So if we had another example, we try to go to server 1, which is server1.anishnaabemowin.com. The workstation is going to go ask this DNS server, do you know the IP address of server 1? It's going to check its local record. And it's going to come up, yeah, it's 192.168.5.2. So then server 2 will reply that address to workstation. Then workstation will send a packet out to the server, and it can then talk to it because it knows its local IP address. Now, say we're at workstation over here and we wanted to access our web server, which is www.anishnaabemowin.com. Now, because this is on the internal network, it's not going to have direct access to DNSE1. This link right here is only for the external DNS servers to use, so they can get updates and basically resolve names so they can use the internet. So what's going to happen is the workstation is going to go to server 2. It's going to ask, do you know where this website is? And server 2 is going to look in its local record. It's going to find it has a host and a alias for www.anishnaabemowin.com that points to the public IP address of 198.108.209.29. So then server 2 will respond to workstation with that IP address, which will then, the workstation will then go out onto the internet looking for that IP address. It'll find it right outside the internet, and then it can successfully connect to the website and use its services. Now that we see how DNS works while interacting with it from the outside, let's take a look inside the server and see what's required to make it work. So right now we're in server 2, which is the server that has the domain controller and DNS on it. We're going to take a look at the zones. The first one is a forward lookup zone. What that does is allows a client to enter a fully qualified domain, and it looks for a IP address that it can use to connect with. So, say our workstation submits www.anishnaabemowin.com. What it's going to do is first, this DNS will look up in its record and see an alias name of www, and that will match the rest of the domain name. And then it'll look in its record and see it points to web.anishnaabemowin.com. Now, right above that record is a host record with web. And inside there lists the IP address, and it'll point to the public IP address of 198.108.209.29, and it'll return that to the client, which the client will use to access the website. So that's an example of how a forward lookup zone works. There's also what's known as a reverse lookup zone, and that works just the opposite of a forward lookup. A client submits a IP address and is looking for a fully qualified domain name. So if it entered in the IP address of anishnaabemowin.com, it'll be 198.108.209.29. The DNS server will look into its pointer record, and it'll resolve that it is its fully qualified domain address is web.anishinaabemowin.com, and it'll send this back to the workstation. Reverse lookups are useful for security purposes. If you get a letter from a fully qualified domain name that you want to verify is actually what it says it is, you can enter in the IP address associated with it, and if it returns the same fully qualified domain name, everything's good. However, if it comes up with a foreign looking fully qualified domain name, one you've never seen before, that's a red flag that there's something going on, possibly a malicious servers trying to cause harm. So it's useful as a security tool. We're going to jump back to Anishinaabemowin, and we're going to try to create a new zone to look at the different options available. The first type is a primary zone, and a primary zone is one that's created with a new zone. It'll point to the DNS server as the primary source of information on the zone, and stores a master copy of the zone records in a data file or database in Active Directory. The next is a secondary zone, and this would be used to make a redundant copy of a server, kind of like with DNSE 2 and 3 in my network. What it will do is get its information based off of the contents of primary zone, or DNS1, and it will basically have another presence online in case DNSE1 went down. There's still an option to resolve names, and it can also be used to help with load balancing. The last type is a stub zone, which is similar to a secondary zone, but it only contains the name server, start of authority, and host records. What it wouldn't have is every host record available to be resolved, only the host for the server that knows, basically like the primary zone in a zone. This is useful if you have a company that works with another company often. This way you can have a direct access to their DNS records. This way you can have a direct access to their main name server, and they can help you resolve names quicker within their domain. So now that we know what zones are, forward, lookup, and reverse, we're going to jump over to DNSE1 and take a better look at the records that are available in a domain, or a DNS server. So the first one available is a start of authority record. And this one's created with every new primary zone. So we're going to go into the properties of our domain and take a look at this record. First off is the serial number, and this is used to keep records in line with secondary servers. So as we can see here, we have a serial number of 25. We're going to change this to 30, and I'll demonstrate how it updates among the other DNS servers. So when we look in our records here, we can see 30 on start of authority. So we're going to jump over to DNSE2, and we can see that our start of authority over here is still at 25. That means we have an outdated copy of the record because the newest one's 30. So if we refresh our screen, we can see that changes to 30. So what it did was it compared the serial number on DNSE2 to what was on DNSE1, and it found it had an outdated copy. So once it realized it was outdated, it went through and refreshed everything. And say if we added a new host record on DNSE1, that would increment the serial number. So once it figures out it's outdated, it would update on DNSE2, and then it would add that new host in. And the same process would occur on DNSE3. It will refresh to the latest copy. Next we have the primary server. This is going to list the server where the zone was initially set up. It'll have the master global catalog, and it'll be the one that updates the rest of the secondary servers. So right here we have the fully qualified domain of DNSE1 here. Next is responsible person. Here you enter an email address of the DNSE or DNS administrator. That way if someone finds an error along the way, they can get a hold of the person and ask what's up about it or see if it can be fixed. The first of the 4 settings down here is the refresh interval. And what this does is shows how long the secondary server has to wait before trying to refresh its own records. So we saw just a minute ago the serial numbers. If those change and it finds they're out of date, it'll update automatically. But if the serial numbers are the same, it'll have to wait, in this case, 4 hours before it can update by itself. This is to minimize traffic on the network. If we had it for 1 minute, it'd be updating every minute and bogging down the network. But setting it at 4 hours gives a reasonable time frame where it won't be using bandwidth resources, but it'll still be remaining current. Next is the retry interval, and this tells the secondary server how long it should wait before trying to reconnect to a server. So say DNSE2 tried to connect to DNSE1, but DNSE1 was offline, so it had a failed connection. It'll have to wait 10 minutes before it tries again. If it fails again, it'll have to wait another 10 minutes, and so on, until it makes a connection. But if it can't make that connection within 7 days, as it shows in the expires after, it'll have to consider its record stale, and it won't be able to resolve DNS queries with its records. It'll have to wait until the primary server comes back online before it can get an updated catalog and resume operations. And this last setting is the minimum TTL, or time to live. Shows how long a record should be stored in cache before it's considered stale as well. Say our client went to yahoo.com and it got its name resolved. If that had a minimum time to live of 1 hour, it could use that IP address for 1 hour. After that time, it would have to then go out and ask its DNS server again for the IP address. This is so if a website's IP changes, it will always remain current in the cache. Now, if that cache was set to 7 days and they changed their IP address in that time frame, the computer or the client won't be able to access the website until that record's resolved after 7 days. Next, we have the name server record, and what this record does is contains the IP address and fully qualified domain name of the servers that will reply to DNS queries on the network. So if we go into the properties and under name servers for Anishnaabemowin.com, we can see there's three name servers in here, DNSE 1, 2, and 3, and it also lists its IP addresses. If we go back and look in our records here, it shows we have 3 name server records, and that relates to the 3 name servers. Our next record is a host record, in this case a single A record. What this does is match a fully qualified domain name to an IP address. So in this case, DNSE1 is at 198.108.209.206, and it keeps going down the line with DNSE2, DNSE3, and the web server, and that each one matches the fully qualified domain name to the IP address. If we were using IPv6 addresses in any of our records, we would have what's known as a AAAA record, and that operates just the same way, but just handles IPv6 addresses. The last record we have in our DNSE1 is what's known as an alias record, and it's a secondary name for a client. So in this case, it's www, and it points to web.anishnaabemowin.com, which then relates to this web host record and the IP address associated with it. Another type of record that's available is what's known as a MX record, or a mail exchanger record. And what this does is allow for SMTP communications to a web server in a namespace. So if we had the email domain at Anishnaabemowin.com, whenever a query comes in, it will point to a specific server that will accept the mail on that domain, on that namespace or that zone. We're going to jump back over to server 2 to look at another record known as a service record. And what that does is points a specific service on a server to a specific fully qualified domain name. In this case, it's LDAP, and it points to server2.anishnaabemowin.com. That would be used for Active Directory and signing in to the domain. And as we can see here, we also have Kerberos and LDAP. Again, those are two services that are used in Domain Controller. And because there's two of them, if we look at the fully qualified domain listing, we can see that there are two servers that are available to take those requests. We have server 1, which is on our VLAN 5, and then server 2, which is our primary controller in VLAN 10. So that's a form of redundancy. If server 2 were to go down, the read-only domain controller in VLAN 5, which is server 1, is still available to take requests and allow users to sign in as normal. If server 2 were to go down, users would still be able to sign in without even realizing there's an issue on the network. If we only had one domain controller and one DNS server and it went down, everything is going to stop on the network until the system admin can get in there and correct what happened. But that's what a server record does, points a service to a particular server that's required. We're also going to look at what's known as a conditional forwarder. Now this is used, if we go back to our yahoo.com example, if there's a lot of clients that use yahoo.com in a network, every time they go to it, it's going to have to go out to the root server in order to find where the web server's at. What we can do here is add a conditional forwarder that points to the yahoo.com domain and the specific IP address that's required. So this way, if say our workstation were to request yahoo.com, it'll come directly to the server, it'll check that conditional forwarder, see it's in there, and it'll go directly to the IP we list in here. There was one downside though. If that IP address ever changes, they're not going to be able to get to yahoo.com until a person gets on the DNS server and corrects it. So it could be, if it happened on a Friday, over the weekend, clients wouldn't be able to get to yahoo.com until Monday morning. So in a case like that, what we can do is set up a stub zone. Now this happens more with local companies that work together, more than say a client going to yahoo.com. But what they can do is have a copy of their other cooperating company's name server and their host record, as well as their state of authority record. And this way, whenever they need to get into their the cooperating company's domain, they just look into that stub record and it'll automatically update which IP address they need to go to. So say if our cooperating company changes their IP addresses around and we try to get to it, it'll automatically refresh with what they did on their DNS server inside of our stub zone. So a stub zone is kind of like a conditional forward, but dynamically updates, which is a nice touch. We also talked about caching a lot, and we're going to look at where that's stored right now. So if we look in our cache lookups, this is on server 2. We can see we have a bunch of folders here, a .com, a .info, .ms, .net, .org. These are all those different top-level domains. Apparently this server is connected to them in the past and put the information it's gathered in these records. So if we look at the .org folder, we can see there's name server records which point to particular name servers on a domain. And then if we look in here, there's a couple host records in here for Blackhole, which apparently this server is connected to before, and it also ties to the IP address in there. So if a workstation or the server tried to connect to Blackhole again, it would simply look in its cache, see it already has this IP address, and then simply go to the IP address. Same with Prisoner. It would see that it has that IP address and continue on. And as we can see, it also holds AAAA records, which are IPv6 addresses, as well as IPv4 and name servers. So the name server, if it knows which domain it's going into, but it doesn't know the exact location of the server, it can forward that request to the name server here, like ns103footprint.net, and then it'll resolve the web server you're looking for, or mail server, or any other address you're looking for. So with a name server, instead of the DNS having to go to root and then the top level domain, it can skip those two steps and go directly to the name server and figure out where it needs to go from there. So the last section we're going to talk about is dynamic DNS. We're going to jump to DNSE1 for that. We're going to take a look in the properties. So in this setting, we can see dynamic updates is currently set to none. Since this is a public-facing server, we don't want any updates to occur. There's also a non-secure and secure option. This means if any server were trying to request an update of a DNS record, be it from a secure server or an unknown unsecure server, it'll go ahead and change the records up in there in the DNS server. So this can be handy because then a system admin doesn't have to go in and update records every now and then when things change. But at the same time, especially being on a public-facing server, things can be changed without a admin knowing and potentially could point to a hazardous site. And there is one more option that's available. I believe it's on server 2. And that'll be the secure-only option. Now, secure-only dynamic updates are available only with Active Directory integrated zones. Because it's an Active Directory, it is considered a safe area within its own naming structure, in its own name zone, namespace. So, if any updates were to come in and it checks out as being secure, it'll automatically update as required. So in a secure-only situation, it's a handy feature. Because again, you don't have an admin that has to go through and manually update all the IP addresses as they change. They will change dynamically and automatically for you. That concludes our discussion of DNS today. I hope you enjoyed.